All right, let's talk about something that connects the crack of a bat hitting a baseball all the way to a rocket gliding silently through space. It's a single, unbreakable rule, the conservation of momentum. You know, it might just be the most powerful law in all of physics, and today we're going to figure out exactly why.
So let's kick things off with a classic riddle, one that really makes you think. Picture this: a rocket, out in the total vacuum of space. There's no air, no ground, literally nothing to push against. So how in the world does it move? The answer, well, it's hiding inside the very law we're about to explore.
Okay, so to really get this, we've got to go back to a law you probably learned in school. Or, let's be honest, a law you think you know. It's a classic for a reason.
Yep, that's the one. Good old F equals ma. Force equals mass times acceleration. I mean, it's the absolute superstar of every intro physics class, right? It's the equation that gets things moving. And you know what? It works beautifully. Well, most of the time.
Here's the thing, and this is super important. F equals ma is kind of like a specialist tool. It's only designed for situations where the mass of the object you're looking at stays exactly the same. Just think about it for a second. When you push a car, its mass doesn't really change. You throw a ball, its mass is constant. So for all these everyday scenarios, it's a fantastic tool for sure. But it's not the whole story.
So, what if I told you there's a more powerful version of this law? Let's unlock the real definition of force. It turns out F equals ma is just a special case of a much bigger, more fundamental rule, kind of like the master version that works for absolutely everything in the universe, all the time.
And here is the big difference, right on the screen. On the left, you've got our classic F equals ma, which, remember, only works for constant mass. But over on the right, that's the general form. Force equals the change in p over the change in time. Now this is the real powerhouse because it works even when an object's mass is changing. So what on earth is this mysterious p?
Well, that P stands for momentum. It's a simple idea, but it's profound. You can think of it as the quantity of motion an object has. The calculation is super easy. Just take an object's mass and multiply it by its velocity. So, a massive truck moving super fast. It's got a huge amount of momentum. A tiny fly just buzzing around? Very, very little.
So what Newton's second law is really saying is this: force isn't just about making something speed up or slow down. It's fundamentally about changing its momentum over time. This is the big idea, folks. This is the master key that unlocks a much, much deeper way of looking at how the universe actually works.
Okay, so now that we have this new, better definition of force, the rate of change of momentum, we can uncover something incredible: the ultimate conservation rule. And it all starts with one simple question. What happens when there's no outside force acting on a system at all?
The logic here is it's beautiful. It's so simple. Check it out. We start with our master law, right? F equals the change in p over time. Then, step 2, we set the condition. What if there are no external forces? We just set F to 0. And when we do that, look at the result. The math just tells us something has to be true. The only way for that equation to work is if the change in momentum, that delta p, is also 0. And hey, if the momentum doesn't change, well, that means whatever momentum you started with has to be the exact same as the momentum you end with.
And boom, right there, that's it. That is the law of conservation of momentum. It's not some kind of magic spell or a weird suggestion, it's just pure logic. It's a direct consequence of how we define force. In any closed system, the total amount of momentum can never ever change. It's locked in.
All right, we've got our ultimate rule. So now let's put it to work. It's time to finally solve that rocket problem we started with. How does that thing actually move?
So let's look at the rocket and all its fuel as one single system. Before anything happens, you can see this in the initial momentum column. The rocket's just sitting there. Everything is at rest. So the total momentum is a big fat 0. Now the law says that after the engine fires, the total final momentum must also be 0. So when the engine shoots that hot gas out the back, giving it negative momentum, the rocket has no choice. It has to gain an equal and opposite amount of positive momentum. It's just balancing the cosmic books.
And when you actually run the numbers on that, you find the rocket recoils forward with a velocity of 5 meters per second. See? It's not pushing against space. Space has nothing to do with it. The rocket pushes the gas backward, and in turn, the gas pushes the rocket forward. It's a perfect exchange. Momentum is conserved. Problem solved.
Now this principle isn't just for things like rockets that are losing mass. It is absolutely perfect for analyzing any kind of collision. So let's take another classic example. A baseball flying in and bam, it meets a bat. We've got all the numbers here. Its mass, its velocity coming in, its velocity going out, and how long the impact lasted. Let's use momentum to see what was really going on in that tiny, tiny fraction of a second.
Okay, first up, we're going to use a related idea called impulse. Now, that sounds a little fancy, but trust me, it's super simple. Impulse is really just another name for the change in an object's momentum. Think of it as the total kick an object gets during a collision.
So we just calculate the ball's momentum right after the hit and subtract the momentum it had right before the hit. That tells us the total change, and that gives us the total impulse, the kick that the bat delivered, 7.5 Newton seconds.
Okay, but here's where it gets really, really cool. We know the total kick, and we know exactly how long that kick took. So using our master formula, we can now figure out the average force that the bat must have put on that ball.
And it's a whopping 750 newtons. To put that in perspective, that's like lifting about 75 kilograms or 165 pounds. And all of that force was delivered in just 1/100th of a second. That, right there, is the power you get when you start thinking in terms of momentum.
So, okay, we've solved a couple of problems. A rocket, a baseball. But what's the big picture here? Why does this one single law matter so much?
It matters because it is genuinely, truly universal. I mean, it doesn't matter if you're talking about planets swinging around a star, or two cars in a fender bender, or even tiny subatomic particles smashing together inside a collider. In any closed system, the total momentum before something happens is always, and I mean always without fail, equal to the total momentum after. It is one of the deepest, most fundamental rules of the game we have ever discovered.
And that leaves us with one final, kind of mind-bending thought to chew on. If the entire universe is the ultimate closed system, does that mean its total momentum was set in stone at the Big Bang and has stayed perfectly, exactly the same ever since? Just think about that. A fixed, cosmic budget of motion, just getting passed around between stars and galaxies and planets, but the total amount never, ever changing. It's a pretty powerful idea. Thanks for joining me.